All right, any questions down here?
Thank you. Thanks, Rana. So I think you had slightly different, the two of you sounded like had slightly different expectations of whether initial LIGO would detect anything. So what did people actually expect that initial LIGO would do? What did you think about that?
So the question was, what were the expectations that the original LIGO would detect?
My expectation was they wouldn't see anything. And so when Barry came on as the director, we met with the National Science Board in the process of him taking over as director. And we had an in-depth discussion with them. And I think that Richard Isaacson was really concerned that I was going to be as blunt as I was, but I felt it was important to be blunt. And I said I thought the odds were that we wouldn't see anything with the initial detectors, and that it was crucial that we move forward with the advanced detectors in parallel with the initial detectors, and that was where the huge payoff would come. And I think, I don't know how widely that was held, but that was certainly my view.
That's not what I thought. I visited MIT in '98, and I was told, I didn't know where I was going to grad school, but I met with Ray, and he said, probably in 3 or 4 years. And I thought, that sounds like a good deal to me. That's a long enough PhD, and probably we'll find 1 or 2 things. And how could it possibly not work? We're just bouncing a laser beam back and forth. How hard could it be? And as the years went by, I think I never lost that optimism. I think I always thought it was probably a few years in advance. And then when I got here, I also would tell that to the new grad students. That went on for probably a decade.
That's the difference between an experimenter and a theorist.
Yes.
How did the initial excitement and then disappointment over Weber bars affect the funding from LIGO? Were there resources that were diverted or direction?
So the Weber played a huge role in getting people to start thinking about gravity wave detection. And I think Ray Weiss and I had the same view on this, that Weber did a great service to the community in that respect. But the fact that it turned out he was not seeing gravitational waves, nobody could replicate what he saw, that had big consequences in some circles, less consequences in other circles. But it was something that hung over the field, certainly, for decades thereafter. And it was part of why it was so important that we really be absolutely sure that teams should be absolutely sure that this was a real detection when this signal came in. So it did weigh on the field, but at the same time, I think it would not be right to fail to give Weber credit for getting the field off the ground and for having the vision that you could really pull it off and be the first person to really start thinking about technologies for the field.
All right, next question. Nobody? Wow, that was quick. Well, I have a question. With the resolution, Rana, that you described of getting better and better, now we're seeing black hole collisions, now we're seeing neutron star collisions. What are we going to be seeing next, if you had to speculate wildly and irresponsibly?
If Kip wasn't here, I might have given different answers, but now I feel kind of...
You go first, and then Kip.
I'm going to see next.
Or what would
You've really put me
surprise
on the
you?
spot. I'll say what I've always hoped to find is, a real smoking gun that the regular Einstein's equations are not it. And I don't think we're that close to it yet, but that's always been my goal since I initially started, was that there would always be this regular relativity that we confirm, and it is as people would expect. But then when you really get, as we're getting there, as the mergers get better and better, eventually you're going to have a merger that's so loud that you're going to hear something which isn't just the relativity, but it's going to be something like the scratch of the record player or the violin player's fingers on the strings or something, but you'll find what's the crust around the black hole and what's really happening there, or what's the noise in space-time, but you'll find out, is there something that's more fundamental than relativity? Is there some kind of microphysics of space-time, or is there some sort of distortion around the event horizon? And I think there's a lot of good reasons to say all of that stuff is so tiny that you're never going to find it. And that's what people tell me a lot. But I say, I don't care what you think, because in the end, nature is what is the arbiter. And if we trust people to tell us what's going to be out there, then we would never get anywhere. And so you have to just have to push the measurement to the point where it's, 1 million times better than where we are now or something like that. And then we'll really find out what's going on.
Amazing.
So let me just trade places with you, Ron, in the following way, that you were expecting unexpected things. I am expecting unexpected things too, but I have been expecting that it would be harder to get to them than you thought it would be. But I do, when I tried to make the case for this field, I always said the most important thing is that somewhere along the way, we're going to discover something that is totally unexpected, that is going to revolutionize our understanding of the universe. I don't know what it is, and I don't know when it'll come. But every time a new window has been opened onto the universe, there have been big surprises. And we've seen some modest surprises so far, but no big surprises. But it could come at any time. And I believe that very strongly. So I keep waiting and hoping, but it may come this decade, it may come next decade. It may come this year, it may come 3 years from now. I don't know when it's going to be. But I'm essentially sure that will happen. It'll be something that we just totally didn't expect.
Yeah, I'm hoping that our group here, who is always combing through the data and learning how to find things that we didn't expect, will do that thing. And we've been kind of looking under the lamppost of finding signals that we know about, and those searches are going on, and they might turn up something. They might turn up something expected any day, but the real great thing is going to be that thing that all of the detectors in the world are finding, but it's just something that we don't have any predictions for.
I also think that your idea of something strange going on near the horizon of a black hole that actually affects the gravitational wave signals that we see, that's not crazy at all. It's not what I expect to happen, but I wouldn't be very surprised if it happens. I've seen on several occasions things that I thought absolutely had to be true be disproved. Like I could never imagine there would be an acceleration of the universe. I had to see it from 3 different pieces of information that were basically very independent before I ever believed it. And I think I'd be much less surprised by LIGO seeing evidence that there's something crazy, unexpected going on near the horizon of a black hole. That will surprise me less than the acceleration of the universe that surprised me. So I think searching for those kinds of things is tremendously important. It will pay off at some point, whether it's going to be that or something else, but I had fairly strong views as to what would be the strongest source, which was right, and when it would come in terms of sensitivity, which was pretty right. But that is quite different from the huge payoffs and the surprises that will be less common than the first thing we saw. But I very strongly back your gut instinct when it comes to the surprises.
All right, you heard it here first.
Kip's seal of approval. Yes.
Kip, you presciently anticipated black holes as the first detections. Did you anticipate them to be as massive as the ones we see?
No. That was a surprise. But there was some attitude that suggested that, among my astrophysicist friends, that suggested that the black holes would not get any larger than maybe 20 solar masses or so, because of ideas about how the stellar evolution goes. And that might actually still be true, and that the heavy things that we're seeing are second-generation black holes from mergers. And that's what LIGO is presumably going to tell us in the next few years as you get more and more data.
That was unexpected, right?
Yeah. But the massive black holes it was unexpected. That was one of the things that was quite unexpected, yeah.
Yes.
So if there's an event inside our galaxy, is it going to be too loud for the instruments to hear, or we don't really know?
So the question was, if there's an event within our galaxy, is it too loud for us to hear?
No, not too loud. I mean, there might be a technical problem that it saturates, like your speaker will saturate if you try to play something too loud, but we always have sensors that are a little bit less sensitive. So even if the main one saturates, because the signal will be something like 100 times louder, or 500 times louder than what we've gotten. And it won't destroy our detectors, it's not that bad. The worst that would happen is the signal would be a little bit distorted, but we would find it.
Or Germany would hear it?
I think so. At least a little detector would find it. Maybe my little one on campus would find it if it was in the galaxy.
Yes.
What do you think the gravitational wave community, including theory and numerical relativity, could be doing now, should be doing now, and isn't doing now?
So the question is, what do you think the gravitational wave community could be doing now, should be doing now, and isn't doing now? No pressure.
That's for you, not me.
I think as we look into the near future, Cosmic Explorer, the next generation instruments, is tremendously important, and we really need support of the gravitational community to push that forward. There's a lot of hesitation in Washington, and though Dave writes, he can certainly say more about that than I can. But I have been quite struck by the very different attitude about moving forward that you find in Washington and NSF today than what we were dealing with in the 1990s and 2000s. It's become much more conservative, much more of an attitude that their job is to put a lid on the field, and you really have to prove yourselves rather than to help us to realize our vision, which is a variant of the same vision as we were having in the 80s and 90s and 2000s. It's just a continuation of the story of creating a whole new way of doing astronomy, of revolutionizing our understanding of the universe. And this doesn't seem to be understood and to be being embraced today. in the way that I think it should be, and I'm just surprised. And so I think doing everything you can do to contribute to getting this moving forward in a vigorous sort of a way is the most important thing for at the present time.
One more question.
Following up on that, is that different outside the United States right now?
Yes,
Yeah.
that's my impression anyway. But other people can say better than I can. That's my impression.
I don't know the answer to that. But I think funding is tight all over the place, for different reasons in different countries. But I mean, you all read the news. So.
But the level of enthusiasm of funding agencies to move forward seems to me to be higher in Europe than it is in the U.S. But it's my impression. Again, Dave can speak to this much better than I can. Dave.
I would say also that you see a lot of investment in China. They're investing heavily in gravitational. Europe is moving ahead with the Einstein telescope, which is their next generation gravitational detector.
So is China doing something now?
What's that?
Is China getting ready to build something?
In space.
Oh, in space.
There's efforts in China for space and ground-based detectors now. I think so. The investment there is pretty strong, and I think a lot of students who have been trained there are now there running those groups, and so it's a good. I think it's a good thing for the international community that we have. This field is, I would say, more collaborative than competitive in the way that we do things, because we all like to share data, because the more detectors you have to share with, the better. So if China makes a great detector, of course, that's great. And I hope that my detector is always the best detector, but I hope that their detector is a close second.
All right, one more question before we go to break. Yes.
So, as a young people in the field, we're in a funny spot. We've detected gravitational waves for 10 years, but there's also funny business going on at the White House. So, I guess, what advice would you have for young scientists trying to get into the LIGO and continue it today?
I didn't get that.
Oh, the question is, what advice would you have for young people trying to contribute to LIGO moving forward, given our political situation?
I think you're better able to answer that than I am, except for the following remark, that I think that young people, I think I'm old enough to have a longer range perspective than most people here. I'm 85. I've seen things come and go, and I think young people should recognize that this situation may be quite different 4, 6, 8 years from now than it is at the present time. And so just keep that in mind. The lifetime of a career is far longer than 2, 4, 6 years. And you have to ride out rough periods. The community has to ride out rough periods. And society has to ride out rough periods. And that's sort of a general remark.
Get back in the lab. That's one thing. Why are you coming to talks? But besides that, I would say I always just feel a lot more positive as each year goes around, because I look around at, it's not just about us and what we're doing here, but the greater world is always pushing the bounds of technology in other areas that seem unrelated. So whatever thing that you're searching for in fundamental physics and astronomy and cosmology, the whole world is working on stuff. And who's to know that day when you're walking down the hall and you're just going to find out that someone's, for whatever reason, has been developing that key algorithm or material or laser that's going to make it work. And if you just, if you live in a community like this, like the world is your oyster. You go around and there's the greatest engineering and science going on in all these different buildings, some of which I've never even been inside of. But every time I go into a new place, I think, wow, I wish I was collaborating with this person over in biology or material science or something. And I think if you do that kind of thing, what you can put together 10 or 15 years from now is going to be way greater than what we have now. When I look back at the kind of things that were around when I started in grad school, it was like dirty kid stuff. Everything was messy and not working that well, and it was tough. But now the amazing technologies we have make it that if you have a really good question about, fundamental science, you can answer that kind of question. And there's a lot of good tools and a lot of good people and a lot of good tools that'll help you figure out what it is you want to do. But you have to figure out what it is you want to do.
And let me make one other remark, and that is that the importance of science for the future of the nation is well understood by a fair number of Republicans in Congress as well as Democrats. They do understand that science and technology underpin our future. And talking with them about that and dealing with them politically, emphasizing this, I think one gets a somewhat positive response from many of them. The particular issue that concerns me, and I think should be concerning them, and will if they begin to think about it seriously, is the technologies of the future. Quantum computing. The seeds for quantum computing were laid by Richard Feynman in 1981 in a lecture that he gave about what quantum computing could do in 81. The seeds for the LIGO type of quantum precision measurement, the squeezing and then frequency-dependent squeezing, those were laid in 1981, initially by Carl Caves here at Caltech. Feynman and Caves were talking with each other, and me, I was in the mix of that. And the seeds were laid here, but then they had to grow to a certain level of maturity before private industry would pay any attention. And you had the gestation period, but then you had the period of maturation that required about 30 years in both cases. And then at that point, it became clear to private industry that they should jump in on it. Both what's called quantum sensing typically, which is sort of a variant of what's being done here in quantum precision measurement, and quantum computing. AI, similarly, also laid here at Caltech, as the Nobel Prize Committee made clear last year by John Hopfield, who was thinking about artificial neural networks, which became the foundation for that. Again, it took about 30 years for that to mature far enough that the private industry got interested. And so you ask yourself, and in all these cases, the maturation process was with federal funding in university labs. Federal funding in university labs. And we've had in the United States this system that creates these new technologies with federal funding in university labs. And what are the technologies of the second half of the 21st century that are being cut off by whacking in half the budgets for science, that will be, in the end, pioneered in China and not in the US, because they're being cut off before they mature, have any chance to mature to the point that people recognize in private industry that, yes, there is something there. And that, I think, is a huge worry and should be a huge, huge, huge worry for Congress and for Republicans as well as Democrats. And I think that message may be beginning to come through with the Republicans in Congress and is playing some role in the markups of the budgets for science in Congress this year already.